Hi, my name is Nicholas Dwork, and today we're going to be talking about the derivative. Note, by default all vectors in Rn in this talk are column vectors. A function is a mathematical machine. You input something and you get something out. And it's denoted f parentheses x parentheses, read f of x. The function's name is f, the input is denoted x, and the output is f of x. As long as you input the same thing, you'll always get the same thing out. The rigorous definition of a function, though, is a three-tuple, an ordered set with three elements, where the first element is itself a set called the domain, the second element is itself a set called a range, and the third element is itself a set called S, which is a set of pairs. There is one pair for each element in the domain. The second element of the pair is a value in the range. Here's an example function. The domain is the set of four letters a, b, c, d. The range is the set of natural numbers between 0 and 8. And S is a set of pairs. Note that there is one pair for each element in the domain. However, not every element in the range is included in a pair in S. And so this is a completely valid function. For each element in the domain, we get an element in the range. We often assign names to function. Below is the function named S. It's an ordered triple, or a three-tuple, where the first set is D, the second set is R, and the last set is the set of pairs S. Another way of writing this is F colon D right arrow R, and this is read F maps D to R. This is followed by such that, and then a rule specifying F of X. For example, F maps the real numbers to the real numbers such that f of x is equal to 2x plus 3. Here is the graph of a function from real numbers to real numbers. And for example, here's a point on this graph, x naught, y naught. And we might ask ourselves, what is the rate of change at the location x naught? Well, one way we can approximate the rate of change is by considering a point to the right of x naught plus delta x. And so f of x naught plus delta x is equal to y naught plus delta y. And we can connect these 2 points with a straight line as shown. And then we can calculate the rise over run of this straight line, and that will be its slope, denoted here by little m. Can we get a better approximation of the rate of change at the location x naught? Well, yeah, we can make delta x smaller, as shown here. And by doing so, we get a better approximation of the rate of change. And so we can keep doing this procedure to get the instantaneous rate of change. And this is the derivative. The definition of the derivative is follows. It's the limit as delta x approaches 0 of f of x naught plus delta x minus f of x naught all over delta x. And it's denoted f prime at x naught. The derivative gives us the slope of the tangent line, also known as the instantaneous rate of change. Though this is true, it's not the best way to think of the derivative because it doesn't generalize. From this definition, we get the following expression. F of x plus delta x is approximately equal to f of x plus f prime of x delta x. And this is true when delta x is small. This is a very good way to understand the derivative. It's going to provide us with a lot of intuition for many different types of functions, which we'll explore during this presentation. This is how we want to think about the derivative. It will generalize to higher dimensions. And so now we can approximate the function at x naught as a line. F of x naught plus delta x is approximately equal to f of x naught plus f prime of x naught delta x. And this approximation is good when delta x is small. Now we'll consider functions of the form f maps Rm to Rn. That is, f accepts vectors as input and outputs vectors. If f is differentiable at x, then there exists a matrix D such that if delta x is small, f of x plus delta x is approximately equal to f of x plus d delta x. And so this agrees with our intuition. This is what we want the derivative to be. Equivalently, we can say that the error is small when delta x is small, where the error is f of x plus delta x minus f of x minus d times delta x. So one might think that the derivative is the matrix D that satisfies the following expression: the limit of the norm of the error goes to 0 as delta x goes to 0. But this is not strong enough because it doesn't equal the rate of change when m and n are both 1. So this leads to the actual definition of the derivative. The definition of the derivative of the function f, where f maps Rm to Rn, is the matrix f prime of x of size m by n such that the limit as delta x goes to 0 of the norm of f of x plus delta x minus f of x minus f prime of x delta x divided by the norm of delta x is equal to 0. And with this definition, our intuition remains. F of x plus delta x is approximately equal to f of x plus f prime of x delta x. Again, remember, in this situation, f prime of x, the derivative of f at x, is a matrix. A special case of this situation is when f accepts vectors as input and outputs a real number. In this case, the derivative is a row vector of size m. In this talk, we use the convention that the gradient is a column vector, so the gradient is the transpose of the derivative. Here's an example of what we've been talking about. Here is a function b. It accepts 3 real numbers as input, x, y, and z, and it's defined as b naught plus g sub xx plus g sub yy plus g sub zz. And so the questions are, what is the gradient of this function? What is g sub x? And what type of gradient is this? Well, in this situation, g sub x, g sub y, and g sub z are all real numbers. And so assuming that b sub naught is a constant, the gradient of f is this. It's this constant vector, g sub x, g sub y, g sub z. And so this is a constant gradient. People often refer to this situation as a linear gradient, but that's incorrect. This gradient is constant. Now, if b sub naught is not a constant, if it itself is a function of x, y, and z, then the gradient of f is defined this way, involving the partial derivatives of b naught. And again, g sub x, g sub y, and g sub z are all constants. Here is a theorem regarding these types of functions. If f maps Rn to R, and it has an extremum at x, then the gradient of f at x is 0. And here's some intuition as to why this is. Let's accept our intuition of the derivative. Then f of x plus delta x is approximately equal to f of x plus f prime of x delta x. And remember, f prime of x is just the transpose of the gradient. So this is equal to f of x plus the gradient of f at x transpose times delta x. Now, since f has a minimum at x, a local minimum, then f of x plus delta x is greater than or equal to f of x when delta x is small. That's the definition of a local minimum. And so this implies that the inner product of the gradient of f at x and delta x is greater than or equal to 0. And this means that the gradient and delta x are acute. That is, the angle between those two vectors is less than 90 degrees. But since delta x was arbitrarily chosen, the gradient of f of x has got to be equal to 0. Another type of derivative for these types of functions is called the directional derivative. So let E be a unit vector in Rm. For functions f that map Rm to R, where m is greater than 1, the directional derivative is defined as follows. It's the limit as h goes to 0 of f of x plus he minus f of x all over h. And it's denoted the derivative of f in the direction of e at x. Note that the directional derivative is a real number. And our intuition remains. F of x plus delta x is approximately equal to f of x plus the directional derivative of f in the direction of e at x times the norm of delta x, where delta x is in the direction of e. And what we're doing in this situation is we're taking a slice of our function through a vertical plane. And this vertical plane intersects x and is in the direction of e. So a point and two vectors define a plane. That's the plane we're talking about. And so we're asking, what is the rate of change of this function if we restrict the function to this plane? Here's the theorem. If a function is differentiable at a point, then all of its directional derivatives are defined at that point. However, the converse is not necessarily true. Even if all the directional derivatives are defined, the function may not be differentiable at that point. Now for functions that map Rm to Rn, there's also a special name for the derivative. When m and n are both greater than 1, the derivative is called the Jacobian. The Jacobian is a matrix of size n by m. What about functions that map matrices to matrices? So here we're discussing functions f that map real matrices of size m by n to real matrices of size u by v. In this case, our definition of the derivative is not applicable. We've generalized the derivative for functions that map Rm to Rn. We will now generalize this further for functions that map one normed vector space into another. So let f map u to v, where u and v are both normed vector spaces. The derivative of f for an input x is defined as the linear transformation L sub fx that satisfies the following. The limit as delta x approaches 0 of the norm of f of x plus delta x minus f of x minus the linear transformation applied to delta x divided by the norm of delta x is equal to 0. With this definition, our intuition remains. F of x plus delta x is still approximately equal to f of x plus the linear transformation applied to delta x when delta x is small. Now, complex numbers are a normed vector space, and so we could use the definition of the derivative developed so far for functions that map complex numbers to complex numbers. But complex numbers are a field, and so division is defined. So we can make the derivative more powerful, and here's how we define it. It's the limit as delta z approaches 0 of f of z plus delta z minus f of z divided by delta z. And we can do this again because division is defined for complex numbers. With this definition again, our intuition remains. We get this approximation that's valid when delta z is small. But because we're using this more powerful definition of the derivative, we get some more interesting theorems. And so here I'll show you the Cauchy-Riemann equations. Consider a function f that maps complex numbers to complex numbers, such that f is equal to u plus iv. In order for f to be differentiable at a point z, it must satisfy the following equations. And these equations here are called the Cauchy-Riemann equations. We get this theorem because of the more powerful definition of the derivative. So we've been generalizing our definition of the derivative for functions that map more and more interesting types of sets or spaces. And so here we're going to talk about a more broad definition of derivative. We can think of a set of functions as a domain. Recall, a function is just an ordered triple, where the first element is the domain, the second element is the range, and the third element is the set of match of pairs. And so we can think of a set of these ordered triples. And we can hope to find a metric that acts like a distance between these functions, between these ordered triples. And so here's the metric. The distance metric we will use is the L2 norm. And the L2 norm of a function is defined as follows. The L2 norm of a function squared is equal to the integral of the magnitude squared of that function. And so two functions are close means that the L2 norm of their difference is small. A functional is a mapping from some vector space to the underlying field. For a functional A, we want some entity that acts like the derivative of before. That is, we want some entity D that agrees with our intuition of the derivative. The functional A applied to f plus delta f is going to be approximately equal to A of f plus D times delta f when delta f is small. And we will now explain what this thing is. Let's consider the definition of a Banach space. A Banach space is a complete normed vector space. A metric space is complete means that every Cauchy sequence converges. So for example, the set of functions that have a finite L2 norm is a Banach space. And this set is particularly interesting because all of these functions are Fourier transformable. And so here we define a new type of derivative, the Frechet derivative. Consider the functional a that maps a Banach space B to the real numbers. The Frechet derivative of a at the function f is the linear functional d sub af that satisfies the following definition. The limit as delta f goes to 0 of the magnitude of a of f plus delta f minus a of f minus the functional of delta f divided by the norm of delta f is equal to 0. And again, this definition agrees with our intuition. Analogous to the directional derivative, for these types of functionals we have the Gateaux derivative. The Gateaux derivative of a functional a that maps b to the real numbers towards h. Now mind you, h here is a function, so we're asking for the functional of a at f towards h is this. It's the limit as epsilon goes to 0 as a of f plus epsilon h minus a of f divided by epsilon. Again, the Gateaux derivative is analogous to the directional derivative. And we say, what is the derivative of a at f in the direction of h? This again agrees with our intuition like the directional derivative did before. A of f plus delta f is approximately equal to a of f plus the Gateaux derivative evaluated at f times the norm of delta f, where delta f is a small scalar multiple of h. And for this approximation to be valid, h must have unit norm. And analogous to our theorem from before, if a functional is differentiable at a function, then its Gateaux derivative is defined at that function. The calculus of variations is the study of functionals of a specific form. Shown here, a of x is equal to the integral from a to b of f of t, x of t, x prime of t, dt, where x is in the domain of a specified here. In particular, x has to be differentiable, defined on the interval from a to b, and the endpoints of x have to be x of a and x of b. And so a question is, what is the Frechet derivative of this functional? Let's find out. Here we have a of x plus delta x. And what we want is this to be approximately equal to a of x plus some linear functional applied to delta x. Well, using our intuition of the derivatives from before, a of x plus delta x is approximately equal to this, where d sub 2 is the derivative of f with respect to the second argument, and d sub 3 is the derivative of f with respect to the third argument. So here we have a of x plus stuff. And that stuff is the integral of the second derivative of f times delta x plus the integral of the third derivative of f times delta x prime. That's the problem. We have delta x prime, but we want delta x. And I should note that delta x is restricted so that the endpoints, delta x of a and delta x of b, are both 0. So how do we convert this delta x prime into a delta x? Well, you use a very common trick for doing so. You apply integration by parts. And when you do that, we get this expression. A of x plus delta x is approximately equal to a of x plus this thing that has a delta x in it. And this, it turns out, is a linear functional. And so this is the Frechet derivative. This is the Frechet derivative of a at f applied to delta x. If a has an extremum point at x, since delta x was chosen arbitrarily, we get the thing inside of the integral must be 0. And it turns out this is a very famous formula. This is called the Euler-Lagrange Equations. This equation is analogous to setting the derivative equation to 0 for functions from R to R. you know that if you have an extremal point for a function from r to r, then the derivative must be equal to 0 at that point. Similarly, if a functional of the form studied by the calculus of variations has an extremal point, then the Euler-Lagrange equations must be 0. That is, it must be 0 in order for x to be an extremal point of the functional a. So what's the big takeaway? The big takeaway is that the derivative provides us with a simple approximation to complicated functions that is good for short distances, and it follows the intuition f of x plus delta x is approximately equal to f of x plus f prime of x delta x. This is true even when f is weird type of functions mapping things like Banach spaces to real numbers. I would like to thank Daniel O'Connor for helping me understand this material, and I'd like to thank you for your attention.